All right, welcome back, everybody. This is the second lecture in our MISU Drought Seminar series. I am Professor Toby Alt from Cornell University, visiting Stockholm this year as a Fulbright scholar. Today, we're going to talk about drought indices. And just to recap from last time a little bit, one of the key concepts that we explored was the idea of drought as an imbalance between supply and demand for moisture. The supply comes in the form of precipitation, snowpack, rainfall, or you can think of it even in terms of reservoir levels or lake levels. And the demand for moisture arises from evapotranspiration by the atmosphere or from irrigation, other agricultural uses, and municipal water uses. Drought indices really are an attempt to normalize that moisture balance equation of supply and demand in a way that is consistent across space and through time. And that's the key concept here. When we're talking about drought indices, what we're trying to do is find a way of normalizing the anomalies in precipitation or precipitation minus the evapotranspiration demands and be able to look at variations consistently across space and through time. We can look at a really simplified moisture balance equation here. On the right, we have change in soil moisture relative to time as a function of the precipitation supply minus evapotranspiration minus the runoff and minus the loss to groundwater. And on the left is the picture that my colleague Greg Peterson sent to me a number of years ago from the San Joaquin Mountains in Colorado. An amazing place. If you ever get a chance to visit it, I highly recommend going there. You can see there's actually, this is like a Where's Waldo thing for those of you who know about Where's Waldo. There's a tree ring scientist named Connie Woodhouse coring a tree somewhere in this picture. You can find her. Congratulations. I like it because it captures a lot of the aspects of what we think about when we think about the moisture balance. This is, on small spatial scales, we're talking about, a few meters or even just, up to a few hundred meters maybe, where the supply of moisture gets partitioned into these different components. So if it's raining heavily here, there's going to be a substantial amount of runoff, but not all of it's going to be lost to runoff. There's going to be some change in the soil moisture. And that change in soil moisture is going to then be further modified by the role of vegetation. Now, when we're using a simple moisture balance model like this, we're usually referring to monthly averages or some longer time steps so that we don't have to worry too much about the lateral flow of moisture in from one grid point or one domain to another domain, and where there's plenty of time for these processes to be parameterized in a simplistic sense. So some little thought experiments here with this moisture balance equation, just in your heads real quickly. You can imagine what happens if on a monthly, say we're talking about monthly data here, over the course of a month, what happens to soil moisture if precipitation is greater than evapotranspiration? Well, to first order, all other things being equal, you would expect soil moisture to increase if on average over the course of a month precipitation exceeds evapotranspiration. The other way around, right? If evapotranspiration is greater than precipitation, then you would expect soil moisture to decrease during that time step. And likewise, number 3 on the right here is, well, what if soils are saturated? Well, if soils are saturated and it starts raining, then you'd expect no change in soil moisture because it's already at capacity, and all of the excess should go into runoff or to groundwater loss. So that's sort of the basics of what we'd expect. And then in the other extreme, I guess I should have included here is, well, what happens if the soils are completely dry and evapotranspiration exceeds precipitation? Well, in that case, you probably don't expect any change because the soils are already completely dried out. One of the key things that we need to think about when we think about soil moisture, especially on monthly timescales or shorter timescales or even seasonal timescales, is the role of memory. In other words, persistence. On the left, I've just drawn this schematically here in this little diagram. You have the precipitation minus evapotranspiration as input. And precipitation varies, if you think about it, on daily timescales, right? It could be raining one day and not the next. Evapotranspiration, likewise, is going to be driven by in a large part by weather, so temperature, wind, humidity, how much demand is there for moisture by the atmosphere. And that means that the precipitation minus evapotranspiration fluxes are going to have variations on short timescales, but they're going to be filtered through the surface layer, the surface soil moisture, which is going to vary more slowly in response to those short-term variations. And in this sense, it looks like a autocorrelation process. We expect that for most regions. It's not going to be true of all regions, of all soil types in all cases, but it's something to be aware of when looking at drought indices in general, when thinking about drought in general, that there's going to be a role for persistence from 1 month to the next month, or 1 week to the next week. And the shorter the timescales, the more important this autocorrelation, this autoregressive behavior becomes. So there it is, your run-of-the-mill autocorrelation model. On the left, we've got x at some time step t as a function of some autocorrelation parameter, and the previous state, the previous time step of x t minus 1. And in an autoregressive stochastic process, we have this term here on the right, just in a statistical sense, taken to mean the white noise term. Here we're thinking of the noise, quote unquote, as the precipitation minus evaporation flux. It's something to have in your mind when looking at soil moisture and in looking at drought indices. Two of the main indices that you will find widely used in the literature to look at drought variations through time, really the first two indices that should come to mind whenever you think about drought indicators, cross space through time, are the Standardized Precipitation Index, SPEI, and the Palmer Drought Severity Index, which I talked about a little bit last time. I will walk you through just some of the basic details and assumptions going into each of these, but to really get into enough depth, I recommend that you look at the reading list at the end here. I'll have a slide for that at the end of this lecture. You can dive into a lot more detail on the algorithms that are used to compute either the SPI or the Palmer Drought Severity Index, the PDSI. All right, so the steps for SPI to start with. So this is a simple index. It was designed to be a meaningful statistical index, so it wouldn't have weird pathological nonlinear behaviors. So it's constructed with the statistical goal in mind of being able to track drought across space and through time in a consistent way. And so the first step in doing this is to take the precipitation data and pool it at weekly or monthly timescales, and then create a climatology for that entire, let's say we're working with monthly data. So we get a climatology for each month. We have a distribution for each January in our data set at a given location, and a distribution for each February, and a distribution for each March, and so on. Once we have that distribution, we fit, in this case, it's going to be a gamma. We're going to fit a parametric distribution to our pooled data for each month from our entire temporal domain. So let's say we've got data from 1980 to 2010, 30 years of data. It's been pooled into Januaries, all the Februaries, all the Marches, and so on. We're going to fit a gamma distribution to that data for each month. And then we have to remap that gamma distribution back onto a normal distribution so that we can determine how far away any given month's precipitation value is from what's expected during that month. And so now we end up with a normal distribution, and the anomalies in that normal distribution are going to be just like a standard Z index, right? So unit standard deviation and zero mean. So now when we remap our data into time, taking into account where in each distribution each data point lies, we're going to end up with a value of -1 that really is one standard deviation away from what's expected at that location. Same with -2, -3. So now we have monthly data at a given location with unit standard deviation and zero mean, and it's normally distributed. And because it's normally distributed via the central limit theorem, we can start aggregating our monthly SPI values together by just simply adding them up, so that you can look at not just the 1 month anomalies, but the 2 month or 3 month or 6 month or 9 month SPI departures. And that gives you an indicator of not just the instantaneous, like meteorological drought, as we talked about last time, or the short-term droughts that might be occurring. You could have a situation where it's a summer that's wet on average, but one of the months in the summer is dry. So the short-term SPI might tell you something different from the long-term SPI. And that's the real power of this SPEI approach, is that it lets you track drought anomalies on different timescales simultaneously. And it only requires precipitation, but that's one of its other strengths. There's an extension of the SPEI that I'll get into in a few slides. That's the SPEI, which also factors in evapotranspiration. All right, so that's the basics of SPEI. You can get into the mechanics of it looking at the literature. But the goal is really to take precipitation, which doesn't have a normal distribution and varies in just how much tends to fall each month throughout the annual cycle, and to remap that into something that can be treated like a normal distribution and used to make a well-behaved statistical index. PDSI, in contrast, was developed originally the 60s, 50s, as an approximation to soil moisture balance in a way that was normalized so that the anomalies could tell you about the severity of a drought or a wet period. So to do SPEI, you have to estimate a couple of key parameters that are descriptive of the climatologically normal conditions, including autocorrelation. Then there's a step where you have to calculate precipitation minus evapotranspiration balance, which means you have to parameterize evapotranspiration, and we'll talk about what methods have been used to parameterize evapotranspiration. Using that P minus E balance and the equation I showed before, you estimate soil moisture balance, update the soil moisture, compute the initial values of the index in like a first pass, and then you go back through once you've computed soil moisture balance and the P minus E for each month. You go back and reassign values based on whether droughts have been unfolding or incipient or persistent. And so that the final index tells you more about the state of the system in a hybrid quantitative and qualitative sense. All right, I mentioned that you have to worry about what type of equation you use for estimating potential evapotranspiration. And a popular one is the Thornthwaite model. In the past, in the literature, you'll find this. It's grown out of popularity recently for reasons that I'll get into in a second here, but you can start to see maybe some of the limitations just right off the bat if you look at what the Thornthwaite model is using. If you're trying to evaporate potential evapotranspiration based solely on temperature, then your first order estimate might be okay, because temperature, we all know that temperature probably in most cases is going to be linked to higher evaporation rates, but that's not the full story, because humidity and wind speed also matter. And it's been shown quite conclusively that the higher temperatures that we expect from climate change, when used in the Thornthwaite model, will dramatically overestimate the evapotranspiration at any given location across space and through time. So we want to avoid the Thornthwaite model if possible, even though it's compelling to use it because it only relies on temperature. For climate change applications, or any application that uses multiple decades of data where the temperature might be changing because of climate change, its limitations make it not very attractive. So you should avoid it if you can. So an alternative that's more common, still relatively simple and better to use, is the Penman-Montieth approximation. You can read faster than I can talk, so I'll let you look at this. Key details to pay attention to here. It's going to include the vapor pressure deficit, which means that you need to know something about water vapor in the atmosphere. So you're factoring in humidity, which is great. It's going to, again, require temperature, but the role of temperature is going to be smaller. You're going to need to know about wind as well, and something about the radiative fluxes. So those are the other important ingredients in the Penman-Montieth equation. In addition to temperature, Penman-Montieth has a role for water vapor, surface pressure, wind, and radiative effects, all of which influence evapotranspiration, all of which are important to have more reliable estimates of evapotranspirative fluxes. All right, so to try to sum up a little bit of our overview of indices, our quick and dirty overview of indices here. Something you'll see on the news here on the left is the percent of normal precipitation. Like, how much of our normal annual precipitation have we gotten either this month or this season? It's pretty easy to compute. The drawback is that it can be a little misleading, especially in regions that have very strong seasonal variability to the precipitation cycle. So if there's a strong wet season and you're hearing on the news, we've only gotten 60% of our precipitation in the end of January. Well, that might not mean very much, because it could just be that like one storm will bring that other 40% a week later. And so because precipitation's distribution tends to be skewed, and you can get a lot of it all at once, the percent of the normal amount of precipitation doesn't necessarily mean that much. It's still pretty widely used, and it's definitely something that farmers and growers will pay attention to, but it doesn't tell the full story. And it's simple in the sense that you only need precipitation data. We talked about the SPEI. The strength of the SPEI is really that it's designed to be an index and designed to be used in the way that indexes are supposed to be used. You can compare them across space and through time. But it doesn't have a role for evapotranspiration. It only needs precipitation data, so that's a real strength. An extension of the SPEI, really similar, basically the same algorithm, but applied to the precipitation minus evapotranspiration balance is been popular. It's a really useful index as well, in addition to SPI, because it does factor in the role of evapotranspiration. But then you introduce the requirement of needing to parameterize evapotranspiration, which means you have to either use Thornton weight. Hopefully you don't do that because of the limitations of Thornton weight that we just discussed, or Penman-Montieth. But either way, you're going to have to rely on a simplification of evapotranspiration that doesn't know anything about the actual soil moisture state, because SPI does not include a soil moisture balance model in it. It's strictly the atmospheric component of precipitation minus evapotranspiration. So be aware of that. Take it with a grain of salt. It also requires more data to be able to estimate those evapotranspiration fluxes. We talked about PDSI, the pro. I mean, the biggest strength, the reason why people like PDSI is it's not that bad, and it's a pretty good approximation to first order at monthly timescales in many regions across space and through time to moisture balance. But it's simpler than computing soil moisture in many contexts, and it can be compared across space and through time. It's also widely used, so any results that you have in PDSI, you can compare to other authors and other researchers' results. The algorithm is quite complicated. You can look at the literature, you can look at the papers and get into the details of the algorithm. It's not a simple series of steps that are easy to implement in your Python code or your MATLAB code. There are code bases out there that we'll share that you can use to compute it, but it's something to be aware of. And it also requires more data. So you need, for Penman-Montieth, you need to actually have those fields somehow. And in many regions around the world, it's not so easy to get humidity data or radiation data. And so you probably have to rely on reanalysis. So maybe ERA5 would be a good reanalysis product to use to compute PDSI more accurately. And then finally on the right, I've included this SC, self-calibrating PDSI, which is superior to the original PDSI because it uses local climate conditions, makes better use of local climate data and available water holding capacity across space, and is therefore more accurate and probably closer to what's actually happening with soil moisture, as opposed to the original PDSI, which just uses a one-size-fits-all approach to those parameters. Same drawbacks of SP PDSI, except that it also has a slightly more complicated algorithm, and you need water holding capacity in addition to the other data sets that you require for PDSI. Okay, so we're going to do this mental exercise now. Those of you who've taken the class know maybe what you want in an index, and those of you thinking about what would you design for your own drought index, you can come up with a wish list. What would make a drought index most meaningful for your particular application? And this is an important exercise to go through, because depending on what you're doing, depending on the research you're doing, there may or may not already be an index. Maybe one of these products already exists and you can just download the data, or maybe at the very least the algorithm exists and you can download the code and compute the data that you want for your particular site or your particular study. But it's also possible that you need to develop your own drought index for your own applications to get at some feature of the research that you're doing. So if you think about that, this is the list that we came up with in class. These are some considerations. Do you want to have open source code? That would be my requirement. I'd like to see it be written in open source code like Python. How will you factor in supply and demand to your index? Does it need to be generalizable? Do you need to be able to compute this index in the same way using data from Sweden or the US or China or Australia or Costa Rica or anywhere else? Does it need to be relevant to plant water across space? And if so, do you need to be able to factor in or accommodate different vegetation types and microclimates? Probably you want it to be consistent through time. How accurate do you need it to be in the extremes? Especially for climate change applications, you'll see that some of these drought indices, once they get pushed to the extreme either wet or dry conditions, those conditions are outside of the range over which they were calibrated or designed, and they start to fall apart. They don't make any physical sense anymore. Do you need to have physical constraints on your drought index? Some other considerations in that point you can look through. And finally, how are you going to handle snowpack? Are you going to handle lags, autocorrelation, delay? You need to. I mean, if you're in a tropical setting, maybe you don't need to. But if you're in a setting like Sweden, you probably do. How are you going to accommodate, or how does your index accommodate soil moisture state? Right, this is an incomplete list, but these are just some things to think about when selecting a drought index. If you're going to go the drought index route, you may have to consider these and other questions about the appropriateness of the index. And a theme that we'll keep coming back to is that there's no one perfect tool for drought research. There are many different types of tools, each of which are powerful in their own right, each of which are useful in their own right. And it's sort of like comparing a saw and a hammer, right? A saw is good for some things and a hammer is good for others, but you wouldn't want to try to use a saw to do a hammer's work, or vice versa. And the same applies to drought research. And what we're going to be talking about for really most of the rest of the course are the tools and their strengths and limitations and appropriateness for different types of questions. All right, here's the further reading. I will wrap up here, and you can write these down if any of them are of interest to you. They will also appear on the class webpage at some point. Thank you.